We're going to finish SU2 and start with the general discussion of Lie algebras with SU3 as an example. But before that, let me discuss some let me complete the discussion of Clebsch-Gordon coefficient and also discuss Wigner-Eckart theorem. So I just wanted to mention one thing about Clebsch-Gordon coefficient, which we didn't have time. So Clebsch-Gordon coefficient. That is the following, that yeah, even before that, I should say something which is familiar to everybody, I guess, is that I can think of in general in a vector space, I can think of a vector transformation as either transformation of the components of a vector or transformation of the basis vectors. Okay, these are equivalent. So this statement is true also in any representation space of a Lie algebra. Okay, so let me give you an example. So let me define some object called a spinor. Okay, the spinor is defined like this. Let me get my notation. Yeah, so E alpha, okay. If you want to be even more quantum mechanicsy, you can like that, and so this object we will call a spinor. Sometimes the U alpha itself is called a spinor, but strictly speaking those are components of a spinor. So, a general vector in the spinor representation vector space, okay, is called a spinor. Okay, and alpha runs over 1 and 2, and E alpha E1 you can take that to be 1 0, and E2 you can take that to be 0 1. So you know these notations, sometimes these are called plus and minus, things like that. And with this notation, U can be written as U plus 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 U minus, and we have defined the action of the SU2 algebra as some operators, okay, which implement the SU2 commutation relations acting on these vectors. Okay, but we can alternatively say that this basis set goes to some it gets transformed into something else, which are linear combinations of these things, and I want the physical vector to remain the same. This is the same as this, like that. This of course means that when alpha E alpha is rotated to these things, then U prime alpha should be rotated by the inverse transformation. Okay, so this sometimes this U alpha to U prime alpha is sometimes called a spinorial transformation, and this has a clear generalization to any irreducible representation of a Lie algebra. So spinorial transformation. And with this understanding, I claim the following statement is true, that so if you take, so you can consider tensor product of two such spinors U and V, okay, and we have last time we have seen how these E alpha, E beta, some combinations of these things behave like spin 2 representations, spin 1 representation, and some other combination behaves like spin 0 representation, right? Is that clear to everybody? That plus, yeah.
So this vector remains same constant if saying you're transforming your coordinate system.
That's right. So either you hold these vectors the same, okay, and transform them. The same effect can be obtained by keeping these U alphas the same and transforming these. Yet another way of saying this is that there's a physical vector which is U, which is independent of the choice of basis. Okay. So if you have rotated your basis, then you must rotate your components in such a way that the thing remains as the physical spinor remains the same. Okay. So so let me just remind you what we found last time by our explicit Clebsch-Gordon thing, that plus okay, was the highest weight state of the spin 1 representation. So this corresponded to this one, and then you apply J minus here and you apply J minus here. Whatever you get and whatever you get here, they must be identified, of course. So this was plus minus plus divided by square root of 2. This is what you get from here. And from here, what do you get? Sorry, excuse me. You get this. This is what you get. We worked out the, so, okay, just to be sure, this is what we are doing. Okay. We are applying d half of J minus on this and this by Leibniz rule. Okay. So when I apply the, this half, the spinorial representative of J minus on this, I get, or let's say on this, I get minus. Well, let me say it the way I did it precisely in, okay. So if I apply by J minus, I get from plus to minus without any coefficient. Okay, plus remains the same. This is Leibniz rule, remember, and this remains the same, and this becomes minus without a coefficient. On the other hand, on this side, I do pick up a coefficient by acting on J minus. This is a spin 1 representative of J minus, and I get this. So as a result, I can take this here. So this is what you get, and the identification was that this identified plus, plus, minus, like this, okay? And you can carry on, of course, and you will get minus 1, minus, minus after adding another, after applying one more J minus. And when you, on this, when you apply J minus, what you get is 1 minus 1. In these things, you have to be careful about the what? So here, of course, there was another guy, which was the minus, but when you keep applying J minus, the other fellow does not come.
No, what I'm saying is, and if you apply J minus on this combination,
yes,
and you will end up with 2 minus minus, won't you? And 2 minus minus, and on the other hand, on the other side, you will have 2 1 minus 1. So the factors of 2 will
Ah.
And if you
Right,
apply
right,
the
right.
Leibniz rule on that thing.
I see. So you're saying when I apply on this, I'll get a 2,
Hmm.
and here from root 2, I'll get another root 2 here, and I'll
Yeah.
get a 2. Everybody agrees with this? Presumably this is what we got last time. But anyway, this is, so as a result, I have the identification minus 1 minus minus goes to 1 minus 1. Okay, so let me write down how it looks in terms of components. So in terms of components, it looks like that. So what I'm doing now is to say that when I consider a bispinner like this, U alpha V beta, okay, so out of these 4 combinations here, okay, 3 constitute a vector, okay, namely which, just we can read it off from here. I have them worked out in my notes, and whoever is scribing this part, they will work out in their notes. So that is the following, that U plus, where is this? So U plus, so I want to find out of these 4 components, there is some vector hidden here, okay, and I claim that if you take care of the Clebsch-Gordon coefficients correctly, then it's just this. This behaves like a vector, okay, where these are the Pauli matrices, okay, and alpha beta, as I said, these are components which go over the range 1 and 2, okay. So let me just say what happens for A plus, for example. A plus turns out to be, as you would expect, is just U plus V plus. A0 corresponds to U plus V minus plus U minus V plus divided by factorial 2. I get a minus sign here. So this corresponds to minus. This is what you will get if you exactly transcribe whatever is happening in terms of the basis vectors. You write this in terms of components, okay, which you can do, right? Something is happening to the basis vectors of the tensor product space. Of course, you can transcribe that to components, okay. And but what I'm saying here is that if you take this combination, okay, and keep applying, so sigma plus, use sigma plus here, okay, so you have some U sigma plus V. What you will get here is U plus V plus, no big deal, okay. And I should say one more thing, this plus and minus in terms of the spinorial indices, okay, you have to be careful about whether you are writing plus, up or down, okay, and there is a distinction between them. So so just remember this, okay. Okay, let me define this notation. I have not defined this notation. The definition is the following, that I have defined what U alpha is, okay, they are the components of the spinor. I have not defined what the lower alpha is. So it is the following, that U alpha is equal to U alpha beta U beta, where this U alpha E alpha beta guys, this is the matrix which is given by 0 1 minus 1 0, okay. Why is this an important quantity to consider? Because this is like the metric in the space of spinors, okay. That is to say, U alpha or V alpha, U alpha V alpha will turn out to be an invariant, okay. Why is that so? Because you have U1, U2, which is the same as U plus U minus, and then 0 1 minus 1 0 and V plus V minus. So that is going to be precisely the anti-symmetrized combination, okay, which we have already said last time, that so this will give you U plus V minus minus V plus U minus, okay, and this is invariant, okay. So this is like this is like a dot product, but in the space of spinors. Remember, in normal Euclidean space, okay, Euclidean 3 space R3, if you have a dot product, okay, that dot product does not transform, okay. This fellow is also some combination which does not transform, it transforms to itself, okay. So that is why this object, okay, is epsilon alpha beta is something that's called sometimes an invariant tensor. This is also, you can also call that a metric. So this combination is now well defined, okay. I know what the Pauli sigma matrices are. So for the A plus component, so remember A plus by our definition is A1 plus I A2 divided by factorial 2. So I should use sigma plus to be the same thing, I sigma 2 divided by factorial 2.
So Pauli sigma with all upper indices, alpha beta is R well-known Pauli matrix.
Yeah.
With all
So
upper indices.
yeah. So in this one, in the I index, you can be you need not be careful about whether you are writing it up or down, because the invariant tensor there is just Kronecker delta, okay. But here, in case of the spinorial indices, you have to be careful whether you are writing up or down, because it changes U1 U2 to minus U2 U1. Okay, so what am I saying? I am saying that check it out, check that this guy transforms like a vector. How? Okay. So just keep writing this for sigma plus, sigma 0, and my definition of sigma 0 is sigma 3. Okay, so this is my definition of these matrices, and check out that this combination gives you U plus V plus for sigma plus. That's clearly a plus, because here we have proved that plus plus gives you the top component of the spin 1 representation. So that's A plus, and similarly the symmetrized combination of 0 spin is it turns out to be minus A naught, and that in fact is the correct object. And then with the sigma minus component, I am not doing this algebra here, you can just check that this correspondence means, when you explicitly work it out, it's this, okay. So if you keep adding by j minus, come down like that, this is what you will get, and if you keep adding by j minus, this is what you will get, okay. So please work these things out, and as a result we have proved this thing, that a particular combination of bispinor which is written by the Pauli matrices, okay, that's a vector. So this is an important result, that Pauli matrices are nothing but Lebesgue-Gordon coefficients, right. So you start with alpha beta, that kind of spinor, okay, and you take a certain linear combination of alpha beta to get the components of a vector. What linear combinations of these? These are sigma I alpha betas. These are nothing but the Lebesgue-Gordon coefficients, right. So Pauli spin matrices are Lebesgue-Gordon coefficients. Those of you who have already done quantum field theory, you are familiar with a similar statement, that psi bar gamma mu psi behaves like a vector. You are familiar with this. So Dirac gamma matrices are also Lebesgue-Gordon coefficients, okay. So you can take psi bar alpha, gamma mu alpha beta psi beta like that. This object behaves like a vector. What does it mean? That means you take this psi alpha psi beta bispinor combination, okay, and you take these guys, okay, you take this particular linear combination of psi alpha psi beta. Okay. Well, it's psi star alpha psi beta. There's in the middle there's a charge conjugation operator that is sitting here. So including that operator and the Dirac gamma matrices are the Klebsch-Gordon coefficients. Okay. So this is and similarly, you know, people who are familiar with the construction of Meson operators, okay, you have some 3 bar and you have some 3 here, and in the middle you have some you know, Gell-Mann matrices and you know, some specific combination of matrices here, and that gives you a Meson operator here. We'll come to that. Okay, so this is what I wanted to say, but please check this out. Whatever I have said here, that please check this out. Okay, this is something that we have already done last time, and this is how, this is the summary of this. All right, good. So that finishes our current discussion of Klebsch-Gordon. We'll come back to Klebsch-Gordon again in terms of the general Lie algebras. Not today, but next time. All right. So now I'll talk about some object called tensor operators and Wigner-Eckart theorem. This is a particularly useful tool in representation theory as well as in quantum mechanics. Okay, and some of you who have already done an advanced quantum mechanics course probably know both these concepts, but let me just remind you. So that's the following. So suppose that you have some operator OI, OA, let me call it first, OA. Okay. So much of what I'm going to say here is from Georgi's book and Landau-Lifshitz. Okay. So this part that I'm going to say here. Okay. So let us say that I have an operator, okay, in some Hilbert space, which has the following property, that when I commute by the angular momentum operators, okay, this gives me a linear combination of these operators themselves, okay, like but up to a linear combination, this is some DAB, DIAB. Let me put the I here, okay, so AB, where these D are some representation matrices of, so what is DI? DI is D of a spin S representation. Okay, so this is a spin S irreducible representation, okay, of the angular momentum algebra. Okay. So anybody has any example in mind of what such an operator is? Sorry? JIs themselves, very good, of course. So that then will be the adjoint representation. Okay, so this will be then the adjoint representation, and for example, it can have in case of angular momentum, it can have the xi operator. Okay, again, of course, xi's are also vector operators. So you can just find out how the various angular momentum operators act on the position, okay, or momentum. Okay, so all of these guys, okay, would transform in a spin 1 representation. Okay, so if I have a vector here, okay, the position vector, let's say, or momentum vector, then it will be like that. Or if I have angular momentum vector, then also these will all transform in a spin 1 representation. Okay. So now yeah, so in my notes I have some proof of how the position okay, it's rather easy. So if you just put in some x j here, then then you know clearly this has some x whatever epsilon I k x k del L, and you act on this stuff, you will find that it corresponds to. So basically, you will find these epsilon I k L's appearing on this side, and epsilon I k L's are just the structure constants of SU2, and structure constants of course provide the representation matrices of the adjoint representation. This we discussed last time. So that's a simple proof that xi's are some such guys. Of course, if you have xi, xj, okay, like the moment of inertia tensor and so on, and various other interesting objects by taking tensor products of x's, or you can have a spin operator. Okay, so far we have been thinking of spinors as wave functions. Okay, but you can have spin as an operator. Okay, we are familiar with such things in the so-called first quantization versus second quantization. Okay, what appears as wave functions, okay, can also appear as fields. Okay, in that case, these guys are all operators, so you can have spinorial operators. Okay, and so on. So anyway, I'll come to explicit examples. One explicit example of Wigner-Eckart theorem in which this is either the position or the momentum. Okay, but you can construct your own. Okay, so one statement, important statement, is the following claim. The claim is that OA acting on a JM state. So we have already used this notation, so everybody knows what that is. So this object, okay, this transforms in spin S cross spin J representation. Okay, this is an important thing. So it's as if this OA can be thought of as a spin S representation state, and this is a tensor product of that with JM. Okay, then I would have this tensor product of representations S and J. Okay, let's see how that goes. Okay, so
what is S?
So I said that this OA guy, okay, it gets rotated among the O's themselves according to a spin S representation.
Or any spin?
Some S. Some S. It could be 1, it could be 2, it could be half, it could be any of that.
This J need not to be.
So then it would be called a spin half tensor operator. Okay. So tensor is a general name. You know, tensor can be a spinor, it can be a vector, anything, anything that transforms in an irreducible representation. In this discussion, I'm just calling it a tensor. Okay.
So when you're writing the left-hand formula, the
Yes.
J's and O's they can be different representations, different dimensional representations.
So for this commutation relation to make sense, I'm assuming that these OAs, okay, act on some Hilbert space, and I'm using some representation of JIs, okay, which are operators in the same Hilbert space. Yeah. Okay. So that all these things like products make sense, okay, and so on. So I'm going to use that now. So this object. So I'm going to prove this. This is what is the claim. I'm going to prove this. that this, so just to say, maybe let me put the S here itself so that people remember what this is. So these operators OA are they are tensor operators of spin S. Okay. Good. Now, so this thing is of course a commutator acting on Jm plus the other way around acting on Ji, Jm. Right. So this, this however, I know that this is ds I AB OB okay, and this object is this is, yeah, so this is in the spin J representation of Ji M prime and OA. So now what I am doing is that first I am transforming this according to the spin J representation which I already know, okay, and then OA acts on that guy. So let me do it in two steps. This is equal to, everybody with me? This is equal to this, okay, because it's just a representation of Ji on this Jm state, but you know these operators are acting on some Hilbert space which can perhaps contain all possible you know representations of various things. Okay, for example, if it has the you know derivative representation, okay, it can act on an entire Hilbert space, infinite dimensional Hilbert space, which splits into various. So in particular, so this could be the spherical harmonics, okay, and these Ji's will act on the spherical harmonics to give you some spherical harmonics within the same J representation. Again, it will simply mix the M index. Okay, so it's some matrix prime acting on M. So this is the linear combination. Now OA will act on them, but now these are just numerical coefficients. So OA will go through, pass through. So it's like this. Okay. So what's happening? What's happening is that if you think of this as two indices, okay, A and M, Ji is acting precisely by a Leibniz rule. First, it is acting on A and not doing anything on M. So that's this part. It's rotating these A's into some linear combination of B's. Okay, and the next term is something in which nothing happens to A, but this M part is getting mixed up. Okay. So that is the same statement as this transforms in the S cross J representation. Let me make it even more obvious. Okay. This A might throw you off balance. Okay. Let me take linear combination of these O fellows, okay, in such a way that these become eigen operators of J3. Okay. Just like if you have x1, x2, x3, these are not eigen operators of J3. Everybody with me? They were not. x3 is, okay, but I need to take x1 plus minus I x2. I have to take these linear combinations to make these eigen operators of the angular momentum generators. Okay. So similarly, these OAs, as they come, they might come in this form. Okay. As a result, this A does not look like an angular momentum, does not look like a J3 eigenvalue. Okay. That's bad. So let's make it that way. Okay. So let's start from some OA, take linear combination in such a way that I get this defined in terms of some rotation. Okay, I'm using the same notation as George's book, and so that these guys, okay, these guys are linear. These guys are eigenoperators of this. That is to say, this simply picks up a Q. So the spin S representation of J3 acts by commutation on O prime Q to give you Q. Is that clear to everybody? Here, for example, x1 and x3, x2, okay, if you acted by J3 on them, nothing, you know, it gets some awful stuff. Okay, x1 goes to x2, x2 goes to minus x1, etc., etc. But if you do this, okay, then it gets a linear eigenvalue plus 1 and minus 1, depending on which sign you take here. Okay, so that's what I have done here. Okay, I have gone to a basis of the space of operators in such a way that these are eigenoperators of J3.
So why do we define eigenoperators in this way? I mean, the common intuition was to just define.
So that the label is the same as the J3 eigenvalue.
No, I mean, instead of taking the commutator, if we just operated J3 on OQ, then we ended up with QOQ was.
It would be some non-diagonal matrix.
I see.
It would be some non-diagonal matrix, just like here. If I act by J3 on x1, you know, it will give you I x2, and if I act by J3 on x2, it will give you minus I x1, and J3 on x3 will give you 0. Okay, so J3 therefore would look like you know, the I minus I 0 0 0 0 0 0. But I can take some linear combination of these x's in such a way that this becomes a diagonal thing. Okay, this we have already done. Okay, all right. So now I claim that this discussion will become much simpler. Let me call, and so these Q guys, okay, are eigenvalues of the J3 themselves, spin S eigenvalues. So what is the range of Q?
Plus minus.
Very good. So Q goes from minus S plus S. That's the range. So now I claim that applying OQ on an operator on a state Jm is representation theory wise very similar to doing the following operation: SQ Jm. Okay, as if I am you know, taking a tensor product of a state, okay, of J3 equal to Q, okay, with the existing operator. So I am multiplying, I am applying by this operator on O prime Q, okay, which is a J3 eigenoperator of label of weight Q, okay. But representation theory wise it's the same as this. Why? So let's do this analysis now on the O prime guys. Okay, so now Q is like an M index. Okay, it's like an M index, and maybe I should have called it, you know, M prime or something like that. So anyway, like that. These now are just a standard representation matrices of the spin S. Yes.
Using J3 is something specifies to this particular issue 3.
Mm.
Otherwise, the discussion on the left hand
Yes, yes,
goes through.
yes.
Now suppose we have, I'm just trying to understand how it will be different for some other group like ESO4 say, where the number of Casimir bits are different. So here you have chosen this thing to be, for J3 it turns out to be an eigenstate,
Mm-hmm.
this OQ prime.
So instead of this S and J, that will be the corresponding representation labels.
Okay, you will just choose the,
I'll have the representation labels. So this O guys, okay, will be given by something called a weight vector, okay, and you know, this spin and the notion of spin S representation will be replaced by a particular label for an irrep.
so you will just take on the right hand side, you will take the ones that are commutating. Suppose you have two rotations which are commutating,
Right.
two planes which are commutating, then you will take just the common eigenbasis for them on the right hand side.
That's correct. That's correct. So in any Lie algebra, I'll first you know, choose some particular set of commuting operators. Okay, the maximum number of them will be given by the rank. Is a Cartan sub-algebra. So I'll come to that in yes.
So that is GIOL commutator.
Mm-hmm.
That is general, irrespective of the.
It is very general. Now what happens is that with this choice of the basis of my O's, it becomes like a little more. So here, for example, DS3 AB is not diagonal. As a result, this A, I cannot say something like A runs from minus S
No, like I'm confused
to
with
S.
So DI is a representation of JI in some spin vector.
Spin S representation. Yes.
So what is this other index S?
S is the dimension of the representation. So this is a 2S plus 1 by 2S plus 1 matrix.
This is not an index, it's a level.
Yeah, this is the label. Yeah, maybe I should use a bracket or something.
No, this I'm still confused. Like, so OB in this relationship is independent of the vector space, this commutation. But OA transform according to some particular spin representation DI something.
Yes, correct.
But this applies in any spin representation.
Yeah, for example, if this guy, okay, was you know, it was like a vector, then it will correspond to a spin 1 representation. This is the stuff that I said by, okay, I didn't quite work it out in detail, but if you apply the angular moment, the definition of the angular momentum operator as a derivative operator and act on x1, x2, x3, you will find that what you will pick up here, okay, are the representation matrices of the adjoint representation or the spin 1 representation. Yes.
Can you also put a label over O's because they transform according to S figure, that is spin S figure. So it becomes more obvious and put a label.
Maybe. This is the full statement, you know. So example is O1A is XA. Okay, and OA 2 is okay. So this A is now a little. This is a composite label. Let's say now. So this is XA, XB, symmetrized, and all that stuff, in which you also take the trace out. Okay, so this is a spin 2 representation, etc. So this is a composite label. Okay, it, but okay. So maybe I should. So you take two of these x's. Okay, take a symmetric traceless tensor out of these things. Okay, and then so there will be you know 5 of them. Okay, there will be 5 of them. So you can label them by a composite label, capital A, running from. So this will be some linear combination of these blocks. This is the kind of thing that we just did for the spinors. Okay, so this is that. Then it will be the spin 2 operator. Okay, and similarly, you know, you can carry on with this. Something is bothering you, which
so this thing tells something about the operator O. Like if as you said, if S is 1, then it says that O behave like a vector.
Yes, basically just see what is the index sticking to this operator. Okay, if it is a mu, then it's a vector. If it is a mu, then it's like a spin 2 object perhaps. It could also be a spin 1 object. If it is alpha, Dirac spinor thing, then it's a spin operator, etc., etc. So how J acts on them, okay, is precisely you know, denoted by this index that is sticking to it. Okay, you can see by the look of the operator which one it is. Okay.
So the advantage you get by going to the eigenbasis of J is that you know now the exact range of in which your Q goes.
Basically, you know what the spin 1 matrices are. Of course, these are also spin 1 matrices, but in a different basis. You can't read off, you can't write, you know, right away what these objects are. I mean, just like how the angular momentum matrices act on x1, x2, x3. Okay, if you have done a lot of group theory, by then you might forget what the in the J3 is in the x1, x2, x3 basis is. Okay. Yeah, so but on the other hand, in the x plus x minus x 3 basis, it's obvious what it is. J3 is a diagonal, it's 1 minus 1 0, 1 0 minus 0.
Say that this transforms as this kind of a tensor product.
That you can say anyway. That you can say anyway. If this is this was the abstract thing before I rubbed it off. Okay, that if you, even if you have A here and Jm, this A is not a J3 weight label.
So that would be, you won't know what that is.
I wouldn't know what it is, but I know that the first term acted only on the A index, okay, and rotated among the A's, and the second one left A as it is, okay, and acted on the M's, okay. But I couldn't make this statement that I am going to make now, that OQ acting on Jm behaves like, in terms of representation theory, and that's the content of the Wigner-Eckart theorem, as we will find, that it behaves like a tensor product state SQJM, J equal to S and M equal to B. So this means that this is J equal to S and this is M equal to Q. Okay. This is a cleaner statement that I can make if I use this basis, which are the eigenbases of J3. Okay. So, and all of these, okay, have counterparts in the higher dimensional, higher Lie algebras. Every one of these statements that I am making today have counterparts in the higher dimensional Lie algebras. Okay, good. Right. In particular, this statement means, okay, so you know, I'm not going to hang around with this ds. Which d it is, you know, by the context it should be clear that if it is acting on this SQ kind of object, it will be the spin S representation of Ji. That is to say, I am saying that when I act by J3 or J plus or J minus or something like that, on this I'll assume I'll use the same symbol J plus, J minus. Okay, it will be the spin S representative. When it acts here, it will be the spin J representative, etc. So let's work out what the so let me give you some small justification of why I am saying this. Okay, let us say that I act by J3, okay, on this. Okay, if I acted by J3 on this, can somebody say what the eigenvalue will be? Q plus M by Leibniz rule. Good. So J3 acting on this will give me Q plus M times this state. Okay. How about here? So J3 acting on this, so I can write the commutator plus the other way around. When I write the commutator, okay, that will be what? That will be just Q. So one term, so let me do it in at least one step. So I'm doing this step here. I'm acting by J3 on this. So J3 acting on OQ. Okay, in my notes I have always kept these primes, but I'll forget about these primes. That is to say, I have chosen once for all a basis, okay, which is the eigenbasis of J3. Okay, so I'll forget about this prime now, with your permission. So it is Jm and OQ J3 Jm. Okay, so what I am doing, I took this state and I am applying J3 on it. Now this object is what? Is QOQ Jm, and what is this? This J3 acts on this to give me M. Therefore, I picked up Q plus M as an eigenvalue . So what have I got? I got the fact that J3 acting on this animal just gives me back an eigenvalue, namely Q plus M, and I have dropped primes. So this state therefore is an eigenstate of J3 with the eigenvalue Q plus M, just like this guy. Okay. So I leave it as an exercise to show that J plus and J minus also does the same thing. Okay, good. Now what are the immediate consequences that you can say from here is that OQ, when, so remember that this is a spin S guy, when OQ acts on Jm, okay, it can generate representations from J plus S to all the way to J minus S. Okay. So this, from the right hand side, I know that this generates what kind of irreps? It generates from J plus S to J minus S, going down in integer steps. Okay, that's angular momentum representation. We showed that how, did we? Yes, I think we did. Yeah. So how this happens? Therefore, it must happen also on the left hand side. That is to say, if I have a spin S operator acting on Jm on a spin J state, then it creates representations belonging to all these states. Okay. So therefore, I can arrive at the following . So from here, let us say I am taking the example of the operator spin S is equal to 1 and the spin of the state. So I will take this example of S equal to 1 and J equal to 1. Okay. So according to what we just said here, so O1, if you wish I should say the spin label, okay. So this is the highest weight operator, O1 acting on 1, 1. So let me say what I am saying, what I am writing here. So I am writing OSQ on Jm for the choice S equal to 1 and J equal to 1 and Q equal to 1 and M equal to 1. So this is the highest weight state, okay, meaning that if you applied by J plus on this, it would be 0, and if you applied by J plus on this, that will also be 0. because it's the same representation as if, you know, the operator, the representation obtained by commuting with operators is the same as the spin S representation matrices. So J plus acting on this guy is equal to 0. Is that clear to everybody? Okay. So this, therefore, okay, good. So now this clearly is a highest weight state of spin 2. Is that clear to everybody? This is like highest weight component of the operator. This is the highest weight state. Now go to this correspondence. So I have a highest weight state here 1, 1, and I have a highest weight state here 1, 1. So therefore, this must behave as the highest weight state of spin 2. So that's 2, 2. Good. So this, I'll write an equality here, 2, 2. What is missing here is a normalization. Okay. I don't know how this guy is normalized. There's an operator sitting here. Okay. So therefore, what I don't know is this coefficient C. In fact, that's all that I don't know. Okay. I can carry on from here to generate a lot of other stuff, okay, by applying J minus on this. So if I apply J minus on this, okay, what will happen is the J minus will act by commutator on this one and act by normal operation on this one. Okay. So let me work it out for you. So J minus, okay, let me ask for suggestions. On in here it's clear what it is. Okay. I wrote something wrong about the square root of 2 in coming from the highest weight of spin 1. That was no. So the 1 guy, when I use J minus, okay, that actually is just 1, 0. Excuse me, it's just 1, 0. It was not square root of 2 was on the other side. Excuse me. Please correct that. Please correct that. So I had plus plus. I had plus plus.
No, that was fine.
No, there is no square root of 2 here. No.
J minus m plus 1.
Is that right?
That's why we.
Okay. All right. Very good. So here I do know that there is a square root of 2. Okay. This guy becomes square root of 2, 2, 1. Okay. So J minus acting on this gives you this.
You get 2
Actually,
What?
2 plus 2, 2 minus 2 plus.
No, there's a simple formula when you act on a highest weight state. When you act on a highest weight state, J minus acting on Jj gives you square root of J times J minus 1. It's just square root of J. Okay, and if J, this is a spin.
I think the initial normalized.
No, there was a 1 over the square root of.
So here, I think what you say is that because in this,
I'll get it right for you guys. Yeah, please correct that. I think 1 when you act by J minus, it gives you 1, 0, not square root of by this rule, that the factor that you pick up here is just square root of J. Okay.
And on the left hand side, you will get a
On
1
the
over
left hand
root
side, you will get a 1 over root 2. As a result, what I had said earlier was correct. So this acting on J minus gives you 1 over square root of 2 minus plus plus minus. Okay, like that. Okay, therefore this becomes that way. All right. So now, what's happening here on this side? This is new. So please tell me.
So that's one.
Right? So there is a commutator term, and there's a term in which this acts on the edge. So you can be blind, and you can say that J minus lowers this index. First, there is one term in which J minus lowers this index, and there is another term in which J minus lowers this index. Okay, these are the two M values, the operator and the state. Okay, so as a result, what I get is this. Nothing happens here. Say, excuse me. And the M value of the operator becomes 0, and the other term is this is 1 and this is 0. Okay. So this is equal to that. This what?
Oh, it's okay.
The same constant. Okay, the same constant. The same constant is carried through. Okay, throughout this stuff, wherever you started, it could be JJ representation.
And we are operating J minus on this O. We are not picking up any extra coefficient.
No. That is so. Let's do this carefully. J minus is acting on that, right? Okay. So one action is by commutator. One. So I'll just drop this S index from now on, and then I have O minus acting on. O1 acting on J minus. So when I act by this, this is what I get. This acts on 1, 1, right? This gives you something linear in O, namely this will give you just O0. Why is that so? You can check that by seeing how J minus acts on a spin m equal to 1 state. That just gives you m equal to 0 without a coefficient. No coefficients here. Okay. So the analysis is pretty much the same as if, you know, this here there is some spin m equal to 1 state sitting. Okay, and it's becoming m equal to 0, blah blah. So exactly the same stuff that we did last time. Okay, as we did in Klebsch-Gordan. The only coefficient, only difference is that there is a coefficient here coming from the normalization of this state. Okay, because 1, 1 is normalized, 2, 2 is also normalized, but some operator is acting on this. Okay, therefore there has to be a coefficient here. What is that coefficient? That coefficient is simply the following. So you do this. You take the norm square of this and norm square of this. So this will be 1, 1, O1, dagger, O1, 1, 1. Because of the existence of this operator in the middle, okay, it's not 1. It's some number. That number is C. But the point is that throughout the representation theory, throughout the irrep, it's the same number that is carried through. Okay. So and you keep going by J minus later on. It's exactly like what we did last time. Okay, just like doing a tensor product of two representations, two spin 1 representations. Let me summarize that discussion for you. What is the big deal of having the same constant throughout? It's the following.
Now, can't you just normalize the full thing so that C is 1?
Sorry?
Can't you just multiply the whole operator by 1 by C so that the full thing is 1?
Oh, but 1, 1 is separately orthonormalized to 1 and 2, 2 is separately orthogonalized.
Multiply the operator O by 1 by C.
I can do that. I can indeed do that. You will see what you get. Okay, so basically what you get is the following. Okay, that these numbers, if you wish, are the Klebsch-Gordan coefficients. This 1 here was the Klebsch-Gordon coefficient, this is the Klebsch-Gordon coefficient, these are Klebsch-Gordon coefficients. So let me just write that down. Okay. So this stuff can be summarized to say the following. 2, 2, 1, 1, 1. Okay. So that is C. Okay. Divided by 2, 2. And here now I replace this by the state that it represents. Okay. So I'll explain to you what I am doing here. And I keep taking this ratio throughout the representation, throughout this irrep. Okay. So this guy is C. So what I mean to say is that this fellow was actually 1 from representation theory. 1, 1, 1, 1 was actually 2, 2 without a number. Now from here, O1 acting on 1, 1 is not quite 2, 2, but is C times 2, 2. So therefore, I have this C business here. Okay? And this will be true at every level. Okay? Now I have, I do this thing, O0. Now I apply O0 acting on 1, 1. Okay. It will form part of this 2, 1 state. Okay. And just like what I am going to write downstairs, this object, so let us see what I am doing here. This guy forms part of this 2, 1 with a coefficient of 1 over square root of 2. Okay. So 2, 1 has a projection onto this with a factor of 1 over square root of 2, except for this defect piece, which is C. This story would have been true for the tensor product of representation. This story is more or less true up to this one. So as a result, if I take this guy, okay, that the projection of O0 1 1 or the projection of 2 1 onto O0 1 1 is more or less the same as the projection of 2 1 onto 1 0 1 1 in terms of states, but the same object. Okay, so I can keep doing this, write the Klebsch-Gordon here, write the operator matrix element, okay, and it's always the same. Okay. So I can, in order to compute all these other operators, I can just compute only any one of them. Maybe I can compute the matrix element of the highest weight operator, okay, and do this, and I don't have to do these things because these are given by just pure group theory. For instance, this object will be given by this Klebsch-Gordon by this Klebsch-Gordon times this one. So in an entire irrep, I have to compute just one matrix element. Okay, so that's the content of the Wigner-Eckart theorem. Okay, so let me write it now more formally and yes.
What about the denominator? Denominator, what does the symbol? It's just the Klebsch-Gordon for that particular.
It's just the Klebsch-Gordon. Yeah. So this notation I have introduced last time. So remember that this is like J1 M1, J2 M2. Okay, these things with some Jm. Okay, so if I take these if I take these overlap functions and sum over the entire range of M1 and M2, the state that I get is Jm. Okay. So that was the Klebsch-Gordon coefficient. So these are Klebsch-Gordon coefficients. These are Klebsch-Gordon coefficients. So you don't keep computing Klebsch-Gordon coefficients, okay, because they are available in the tables. You can have some Mathematica package perhaps somewhere for Klebsch-Gordon coefficient. You just compute only one operator, matrix element. Okay, everybody else is given by group theory. Okay, so let me write down in one version of Wigner-Eckart theorem, which is the following. That act by OQ on Jm and find the projection on some state where J tilde is something that is, okay, this is S, this is S. J tilde is something that is obtained by the tensor product of J and S, okay, and I divide this such as these divisions that I am doing here by what? The Clebsch-Gordon, namely SQJM, okay, and this is independent of at what level of J3 I am at. Okay, so this in fact is independent of, this is independent of Q and M. So you can do this at your favorite place, maybe the Q equal to 0, maybe the simplest thing to do, okay, and then you take this matrix element. Everybody else, okay, is given by just group theory. I am assuming that these are known objects. Okay, these Clebsch-Gordons are known objects. So you just compute this, for example, you know, at well, of course, one thing is that, you know, there is an angular momentum. So there, okay. So let me say what are the things that it tells you already. Okay. The first of all, this is independent of QM and is also satisfies, of course, this is more trivial. We have already proved that this is a J3 eigenstate of eigenvalue Q plus M. Okay. So therefore, this K must be Q plus M. Okay. So this is not only you know, an independent quantity, independent of QM object, but it's of course also proportional to this Kronecker delta. Okay. So this is a selection rule. This is a selection rule. It says that if you have some you know, electron in a you know, sort of 2s state, okay, and kicked by a photon which carries spin 1, okay, then you have to take it to 2p, for instance. Okay, you cannot remain at 2s. Yes. That selection rule, of course, comes from the Clebsch-Gordon coefficient itself. Yeah, indeed. So first, I should say that that's a good point. First, I should say that the numerator, okay, is non-zero, okay, when k is equal to Q plus M. When it is non-zero, then okay. So let me you're right. There's a Kronecker here, then there's a Kronecker here. Okay. So the numerator, first statement is that the numerator, this guy is proportional to this Kronecker delta. So this is what is called a selection rule. Once the selection rule is done, you would want to find out the transition amplitude, okay, when the photon comes and kicks you. Okay. So this is how you can get it. I'll work out some. Namely, that there's a lot of stuff that you can do just by group theory, which is all known stuff, and whatever operator that appears here, you just take one, you know, your favorite representative of that. Maybe you can take the spin 0 guy, spin 0, okay, and you compute, you know, in some. So take everything your favorite, okay, M equal to 0, okay, and of course, you know, one is assuming that this is being done for a particular J tilde. Okay, you have to take the same J tilde, and you know, this combination has to remain the same. Okay, then this is independent of Q and M. Okay, So all such numerators can be obtained from any one of these things. Okay, and then you do this for 0 maybe. Well, this may not always be possible because your denominator can be 0. Okay, so I'll give you an example. It's important to do this example. Okay, so this is called the Wigner-Eckart theorem. This is called the Wigner-Eckart theorem. Wigner-Eckart theorem. One element of this is the simple one, which is the selection rule, namely that k has to be equal to q plus m, and the other one is about what it is. Okay. Now there can be other quantum numbers. Okay. For example, in case of the hydrogen atom, there could be a principal quantum number here, okay, and another principal quantum number here. So initial state might have some n, and here it might be n prime. You have to take the same guys, okay, n and n prime here. Then it is independent of q and m, but it can depend on n and n prime. Okay. So let me give you that that notation here. So so let me just say that you should look for a particular section of Landau-Lifshitz where this is section 29, where you have formulas for such things. So let me say and even more formally what this is. So suppose that I have some other quantum numbers alpha and beta here. Okay, then what is the full content of Wigner-Eckart theorem is the following. J m alpha and this object is proportional to the Clebsch-Gordon. Okay, it's proportional to Clebsch-Gordon, and the Clebsch-Gordon part does not contain this, and you have S Q and J M. So this is the group theory part, and there is something which is independent of this Q M business, and it is given by this double bar notation. Sorry, excuse me. It is this and O times J alpha. This is the full story. That is to say, the M and Q dependence of this matrix element, okay, are in some group theoretic stuff that's known. Okay, the rest of it can depend on these other quantum numbers like alpha and beta. Okay, and it can also depend, of course, on J and J tilde. And this is called a reduced matrix element. This is called a reduced matrix element. What is the import of this? The import is that you can compute this reduced matrix element by taking your favorite fellow here, favorite example for Q and M, okay, and this part is known. Therefore, you get the reduced density matrix, reduced matrix element, excuse me. And once you do that, then of course everybody else you get. Okay, so how many matrix elements are there? Hell of a lot of matrix elements. For all values of Q and for all values of M. Okay, you get them just by doing one matrix element computation. So that's the power of this So this is the other statement of Wigner-Eckart theorem. Okay, there is yet another form which is also quite powerful. So this is how we will find Wigner-Eckart theorem statement in most places. There are some other textbooks which say the following. That is also quite nice, which is that you take two different operators, okay, like one could be momentum, the other one could be position or something, two different spin 1 operators, so two different spin s operators, okay, and you just divide them. So AQ like that, and JM alpha, and divide by another guy okay, and this ratio is independent of K, Q and M. Okay, why? Because the group theory cancels. Okay, the group theory just cancels out. So as a result, it says it's some stuff like J beta AQ just A. It's not Q or S or something like that. Well, S, it still has the S label, okay, like that, and B. So it's a ratio of the reduced matrix elements which are independent of M and Q. Okay, so you can see that there's a universality, okay, of matrix elements of various operators, provided that they have the same spin. Okay, so different tensor operators having the same spin has this universality. Once you have done matrix elements of position, you don't have to separately do matrix elements of momentum or angular momentum and so on and so forth. Everybody has do this. Okay, all right. I mean, in the sense that once you have to do. Okay, good. So let me just give you one example of. I thought that I would start with C3 today. So it's the following, that how many people know this already? The application of Wigner-Eckart to radiative transition, dipole transition. Okay, everybody does. Okay, I'll skip it. Okay, all right. So, okay, so then I'll just begin, with a general discussion. I'll just take maybe 5 minutes more. Is that okay with everybody? Not more than that. All right. So, now I'm back to general. No, so maybe everybody knew everything about the Wigner-Eckart anyway. But maybe not a detailed derivation, whatever. Okay, now, so what I'm going to discuss are roots and weights. Okay, so these weights are pretty much like the M values of J3 of SU2. That concept gets extended to eigenvalues, simultaneous eigenvalues of several commuting operators in case of Hartley algebras. First, let me get some definitions out of the way. So, compact Lie group or Lie algebra So basically, you can go back to the definition of the Lie group. A Lie group is a topological space, okay, and as a topological space, it is compact, okay. So, but for this discussion, it's neither here nor there, okay. So it's true, this statement, but the property that we are going to use most is that the killing form, okay, in this, so there is an invariant bilinear form in this Lie algebra. So I am going to talk about an intrinsic property of a compact Lie algebra. Okay, what is that? So let me say what we are talking about. So any Lie algebra has an adjoint representation. That much is clear. So it has a finite dimensional matrix representation. Okay, at least one, namely the adjoint representation. Okay. Therefore, I can define products of generators, products of basis elements, or products of elements of the Lie algebra. Just take the corresponding matrices, and I can take a trace. Okay. So I have this Lie algebra. I have two elements, and I define the following thing, which is trace the adjoint representation matrix of X and the adjoint representation matrix of Y, okay, and take a trace. This is also sometimes called trace adjoint X, Y, okay, where it is understood that X and Y are taken to be the adjoint representation matrices. Okay. So for a compact Lie algebra, the mathematician's definition is that this is negative semi-definite, and our definition will be that it is positive semi-definite, okay, because we will multiply these x's by a minus I, okay. But since we are doing some mathematical definitions, we say that this is negative semi definite. What does it mean? That means that if you write down the so for example, if you have some basis like TA, and define TA, TB, call it GAB, okay, then the eigenvalues of this will be negative semi-definite, okay, and when you multiply each of these guys by some I, it will be positive semi-definite, okay. This is one property which is going to come in handy for compact Lie algebras, and the stuff that I said about topological space and compactness, etc. Let me give you an intuitive picture of what a compact group is. Okay, going back to the Lie group, it's like the parameter space of the group is compact or non-compact. That's the issue. For instance, if you have the group of Euclidean rotations, okay, the parameter space is compact. Okay, some angles. Okay, so that's a compact Lie group. On the other hand, if you have boosts, okay, the boost parameter, okay, can be any real number. Okay, so that's a non-compact space. So as soon as you have some stuff like, so for example, SO3 versus SO2, 1. Okay. So which one is compact and which one is non-compact? Because SO2, 1 has a boost in it. Okay. So it has angles in it has boosts, and it shows up in the some Minkowskian signature of this GAB for SO21. If you compute this bilinear form for SO21, it shows up as having some plus plus minus or some such signature. This metric.
I'm asking the question that for non-compact Lie groups,
Yes.
in general we have no such comments that we could have some zeros also. But you just said that for SO, say R comma S, so is it specific to SO R comma S that we will get something like no zero on the diagonal, it's just plus or minus?
Oh no, you can always have, so for example for SO21, okay, in the basis that we have, for example, or if you take SL2R, where you can actually compute it easily because it's a J plus, J minus and J 0. So there you will have some stuff like 0, so I did it last night. Yeah, I can diagonalize it. When you do that, you will have, I did that yesterday, you will have 2 pluses and 1 minus. Yeah, or in a physicist notation, you will have 2 minuses and one plus.
My question is that we would have ended up after diagonalizing, we could have ended up with something degenerate, like some zeros are sitting.
Yeah, good. So good. So that's another concept. So if you have compact as well as semi-simple, okay, then
If you are assuming compact, you have already ensured that this is negative semi.
that's right. So this concept which I'm coming to, that it's negative definite for a semi-simple Lie algebra. Okay. So but before that I have to tell you what a semi-simple Lie algebra is.
Semi-simple
Okay.
will already ensure that it is non-degenerate. Okay, then you will ensure that either plus or minus.
That's what, right. So very good. So the why is this an important concept at all? To have some metric without 0 eigenvalues, or a metric with only one signature eigenvalues. Okay, negative definite or positive definite, that depends on this convention of whether I am having i's multiplying this here or not. So it's the following, that it's taking much longer than I thought. Let me just prove only one result, that if you have this feature, okay, and I will also assume that there are no 0 eigenvalues, so that is an invertible metric. So I'll introduce the notion of semi-simplicity, but next time. What I'm going to show is that FABC is completely antisymmetric. Okay. The existence of a negative definite negative semi-definite inner product. Okay. So I will, by the way, I'll call this thing x y. Okay. So the existence of such a thing will imply for me that FABC is completely antisymmetric. Okay, how does it work? So basically, remember that so this is using mathematician's notation. This is FABC TC. Okay. And now let me assume that TATB. Okay, let me say that I have chosen a basis of I have chosen a basis in such a way. This guy is given by lambda AB. Okay. Basically, GAB okay, is some negative semi-definite matrix, I can always choose a basis in which this is diagonal, okay, and then TATB will be given by some minus lambda delta AB. Okay, these are the eigenvalues of this metric GAB, and I can rescale each of my generators TA in such a way that in general it could have been some minus KA delta AB, okay, but by rescaling each of the generators depending on A, making an A dependent rescaling, I can make all of them to be the same. So let us say I have done that. Now I can read off what FABC is, which I couldn't do before, okay, without this metric business, which is that I will do the following. So I will take TC. So I am taking a scalar product of this equation with this, okay, and TC, by the way, there is no summation over, so this object, okay, let me do this with D here, okay, TDTC. This is minus lambda delta CD. Okay, so what I get is FABC minus lambda FABD. So therefore, the structure constants are now given just in terms of some object like this. Okay. So now, so let me write this once more and replacing D by C. So FABC is equal to minus 1 upon lambda of this object. Now I will write down this inner product in terms of traces in the adjoint representation. So everything is an adjoint representation matrix, let us say. So this is trace adjoint of TC, TA, TB. This. Now we know that the antisymmetry in A and B is obvious. Okay. But I want to claim that is also antisymmetric in B and C now. Okay. Why? That is by using the cyclicity of the trace. Okay. So this object is also the same as TA, TB, TC. So within the trace you can cyclically permute, okay, all objects. So therefore now it is antisymmetric in B and C. Right, and similarly it is also antisymmetric in the other combinations. So it's TB, TC, TA. So it's also antisymmetric in A and C. So therefore it's completely antisymmetric. What is the big deal of that? The big deal is that the FABC matrices, remember, so the FABC matrices are the adjoint representation matrices. Okay. So therefore FABC is the same as add TA BC. By using the antisymmetry property, we found that is the same as minus add TA, and these FABCs, okay, as we have emphasized in the first lecture, that they can be taken to be real, because we can take a real Lie algebra here. Okay, that was the big deal about this, taking the antisymmetric combination instead of IT, taking this. The FABCs are real structure constants, and therefore these are real objects. So therefore now I got this. Therefore the adjoint representation matrices are anti-Hermitian. Therefore the adjoint representation matrices a la physicists are Hermitian. Okay. So if I take the physicist thing here, physicists, okay, then it will correspond to, so let me not belabor the point, it's obvious here. So the TA adjoint representation, adjoint dagger is equal to TA adjoint. Now this is all of physicists. So these T's and are related to that T by some factor of I. So therefore we found that compact Lie algebra implies that the adjoint representation is a Hermitian representation, is a representation in which the generators of the Lie algebra are realized as Hermitian operators. Okay. It turns out that for compact Lie algebras, any representation. So there is a result quoted in Georgia's book that any representation, not just the adjoint representation, but other representations as well, are a representation in terms of Hermitian operators. There's a further claim, which is that for irreducible representations, these are also finite dimensional. Okay, so anytime you have an infinite dimensional representation of a compact Lie algebra, it's basically splittable into irreducible representations, each of which are finite dimensional. So the first one is that the any representation, okay, is in terms of Hermitian operators, and the second is that if it is an irreducible representation, then it's finite dimensional. Okay. So I don't know the proof of this. This is, I'm just quoting Georgia's book. So anyway, next time we will construct representations of these objects. Yeah. So yeah, there's a particularly simplifying notion of a Lie algebra. It's called a simple Lie algebra. Well, obviously, simple has to be simplifying. So it's the following, that there is a notion of, so that's the last thing that I'll say today. There is a notion of an invariant subalgebra, which is the following, that suppose that you have a subalgebra H of G, okay, then if it so happens that any x in H, okay, and any y in G implies this, okay, that x commutator of y comes back in H, okay, then this is called an ideal or an invariant subalgebra. So for a simple Lie algebra, okay, there is no such thing other than H is G itself, or H is a zero vector. Okay, those are the two trivial invariant subalgebra. Yes.
Does it mean that the group generated by the subalgebra is a normal subgroup of the entire group generated by G?
Yeah, barring some global topological things, it is roughly.
Universal cohomology.
That's right. Yeah, yeah. I think you have, that's right. But that's the idea. Very good. So okay, so this, and then there is a notion of a semi-simple Lie algebra. What is a semi-simple Lie algebra? Is that it's something which is just a direct sum of simple Lie algebras. Okay, except that you have to make sure that it doesn't have a U1 factor. Okay, it does not have the Lie algebra of U1 in it. So it's a direct sum of non-abelian yeah, it's a non-abelian simple algebras. So for instance, U3, okay, is not a semi-simple Lie algebra, because U3 can be thought of as U1 plus SU3 in terms of Lie algebra. In terms of group, it is U1 cross SU3. So the U guys, okay, are, but you can handle them separately. So
usually not referred,
So if you look at some of the proofs, okay, you have to put in a lot of exception, this yeah. So when we discuss roots and weights and so on and so forth, if you exclude the u1s, okay, life is much cleaner. So okay, next time. So next time what we will do is to construct a representation of compact simple Lie algebra by exactly the highest weight representation. It will start from somewhere and it will go all the way up to something, okay, by using lowering operators, okay. And just like in SU2, there is a restriction on this J label, okay, of the highest weight, okay. Namely, the highest weight has to be half times an integer, okay. There is a similar statement, okay, in any compact simple Lie algebra. We will prove that, and that will lead to some classification, etc., etc. All right. So on Tuesday.